Hi everyone. In the previous section, we have introduced the concept of cardinality. In this section, we will study a few more examples, illustrate the idea of showing two sets having the same cardinality through construction of bijections. Typically speaking, there will be two steps involved. First, we should construct a function from one set to another. Second, we should show that this function thus constructed is indeed a bijection. So let us take a look at our first example where we want to show that the product set n cross n and n itself have the same cardinality. Here, the construction we're going to introduce is the contour pairing function, under which an ordered pair of natural numbers pq is mapped to the natural number p plus q multiplying p plus q plus 1 divided by 2, then plus q. At the first glance, this formula might not make any sense. To understand its behavior, let us try to compute the function values for the first few instances of ordered pairs in order to develop some intuition. As we can see, starting from 0, 0, we see that 0, 0 is mapped to 0, 1, 0 is mapped to 1, 0, 1 is mapped to 2, 2, 0 is mapped to 3, 1, 1 is mapped to 4, 0, 2 is mapped to 5, 3, 0 is mapped to 6, 2, 1 is mapped to 7, 1, 2 is mapped to 8, 0, 3 is mapped to none, and so on. From there, we can see what this function is doing exactly. Indeed, from these initial computations, we see that the meaning of this function is to enumerate the ordered pairs on each diagonal, starting from the northwest corner. There is only 1 point on the first diagonal, 2 points on the second diagonal, 3 points on the third diagonal, and 4 points on the fourth diagonal. In other words, to determine to which natural number a given ordered pair PQ is mapped, we only need to go through 2 steps. First, we will compute the total number of points contained in earlier diagonals. Second, we got to see how many shifts we need to perform starting from the leading element of the current diagonal. Such information, though, is completely reflected in this function formula. Once we're given an ordered pair PQ, we can compute P plus Q, which stands for the number of earlier diagonals which have been completely taken into account. The first diagonal has 1 point, the second diagonal has 2 points, the third diagonal has 3 points. As we have observed before, there are precisely n points on the nth diagonal. Hence, by summing up all natural numbers from 1 to p plus q, we obtain the total number of points on the previous p plus q diagonals. That is, p plus q times p plus q plus 1 over 2. This is precisely the number of points prior to the leading point on the current diagonal. Also recall that the first element is mapped to 0. Thus, this leading element on the current diagonal is mapped precisely to p plus q times p plus q plus 1 over 2. Finally, standing at the leading element on this diagonal, in order to reach pq, we have to shift precisely q steps. That explains the plus q term in this formula. The rigorous justification for the bijectivity of this function involves nothing more than some routine algebraic manipulation, and we leave the audience to verify the details. Next, let us turn to our second example, where we want to show that the left open, right closed interval 0,1 and the open interval 0,1 have the same cardinality. As before, we want to construct a bijection. Here, for the construction of the bijection, we will follow a divide and conquer strategy. To begin with, let A be the set consisting of all inverses of positive natural numbers. That is, 1, 1/2, 1/3, 1/4, and so on. Also, let B be a proper subset of A, which consists of all inverses of natural numbers starting from 2. In other words, set A and set B differ from each other only by the real number 1. However, notice that the 2 intervals also only differ from each other by the same real number 1. If we consider the following 2 set differences, namely the left open, right closed interval 0,1 set minus A, and the open interval 0,1 set minus B, then clearly these 2 are identical. Now let us define our piecewise bijection. First, we define a function f from A to B, such that for each positive natural number n, f sends 1 over n to 1 over n plus 1. Clearly, the function f defined here has a very similar flavor to the shift function we have introduced in our discussion of the Hilbert hotel, and is naturally a bijection. Now, their complement in these 2 intervals respectively are identical. Thus, the identity map naturally serves as a bijection between them. Finally, we can define our function h from the left open, right closed interval to the open interval in a piecewise manner. If x is in A, we follow fx. If x is not in A, we follow gx. Since f and g are both bijections, so will be h. As a consequence, these two intervals are of the same cardinality as well. Our last example connects all subsets of a given set and all indicator functions of those subsets. Recall that given a set A, PA stands for its power set, which consists of all subsets of A. 0, 1 to the power of A, on the other hand, consists of all functions whose domain is A, whose codomain is the set consists of 0 and 1. We want to show these two sets are of the same cardinality. To this end, we consider the function f from PA to 0, 1 to the power of A, which sends each subset S of A to the indicator function of S in A. Now that an indicator function achieves either 0 or 1, it indeed belongs to the codomain of f. In other words, our function f is well defined. To get some feeling on how this f actually works, below we have provided a figure illustrating this correspondence when the set A consists of only 3 elements. One can see directly that in this simple case, our function f is indeed a bijection. Now, to show that f is indeed bijective in general, we can consider another function g, whose domain is 0, 1 to the power of A, whose codomain is a power set of A, such that given any function h from 0, 1 to the power of A, we send this function to its preimage of the singleton set 1. We can easily verify that f and g are inverses of each other. In particular, since f has an inverse, it must be bijective, which in turn implies that these two sets under consideration have the same cardinality.